So before proceeding to from Hamilton-Jacobi equation to Schrödinger equation, we need to revise well first. The wave equation, it's an exercise from applied mathematics. Okay, it will take about 10 minutes, but it will be very useful, and we will understand, it will help us understand the basis how Hamilton-Jacobi equation is used to derive Schrödinger equation. Okay. طيب okay. So what is the wave equation? It's a quick revision. This is the wave equation. Phi capital here, it should describe a wave, and it's written as phi tt minus c squared phi xx is equal to 0. Why this is called the wave equation? Because it's well known from mathematics that phi, which is originally a function in x and t, can be expressed in terms of a single variable called zeta, where zeta is equal to x minus ct. C here is the square root of c squared, of course, and it's called the wave celerity or the wave speed. So why this is correct? It can be well proven. For example, try to get phi x, partial phi by partial x in terms of zeta. Using the chain rule, partial phi by partial x will be partial phi by partial zeta multiply partial zeta by partial x. Zeta here is x minus ct, and it's easy to derive that partial zeta by partial x is equal to 1, and partial zeta by partial t is equal to negative c. Okay, so zeta x, simply zeta x is equal to 1, so partial phi by partial x will be equal to partial phi by partial zeta. Fine. Now, what about phi xx? It is partial x of phi x. Again, we will use the chain rule, so partial x, which is outside the bracket, will be partial zeta multiply zeta x. Okay, and we have already derived that phi x is phi zeta, so this will be phi zeta zeta, it will be phi zeta zeta multiply zeta x, and again zeta x is a 1. For phi t, you can easily verify that it is negative c phi zeta, and phi tt will be equal to c squared phi zeta zeta. And when you substitute with phi tt minus c squared phi xx, which is the original equation, with the new expressions in terms of theta, you will find that the partial differential equation is satisfied automatically, okay, without knowing the exact expression of phi as a function in zeta. But again, since phi, if we assume that phi is a function in zeta, this equation will be satisfied. Okay, so someone can argue, fine, we believe that phi is a function in zeta, but why we call it a wave? Because if you say that phi is equal to something x minus ct, that means that phi is a traveling wave solution, because we understand from basic calculus that if you subtract some fixed quantity from this coordinate, it means that you are shifting the profile to the right, as it's well illustrated in this sketch. Okay, so it's a traveling wave traveling with a celerity c. Now next we are going to do some more math, okay, because we will try to simplify a little. We know that phi capital is a wave, so we'll decompose it or try to separate the space dependence and the time dependence. This is phi capital, it's function of x and time. Phi small will be function in x small, and we are introducing here the exponential, and we are introducing I is the imaginary number, square root of the negative 1. And as you remember, e power negative I omega t is a cosine omega t minus I sine omega t. This is the well-known de Moivre's relation, and it will be useful since we are speaking about a wave that's oscillating to introduce the trigonometric identity or the trigonometric functions. And working in terms of the exponential is very much efficient and helpful and simplifies the algebra. So again, using this expression into the original wave equation, we get this long expression that you could see it here. For example, phi tt, you will get negative I omega multiply negative I omega, as you have seen, it's all squared, multiply the original expression. And phi xx negative c squared, you will get the second derivative here. And now comes the most dramatic part. We will cancel out e power negative I omega t from both sides, and we get this irradiation negative phi omega squared negative c squared phi xx. And then we will make an important step. We will divide both sides by c squared. Omega squared over c squared will be written as k squared phi plus phi xx is equal to 0. K here is equal to omega over c, and omega, if you remember, it's called 2 pi over the period, and c is the wave celerity, and the wave celerity is equal to what? Equal to the wavelength divided by the wave period. So the wave period cancels, and we get 2 pi over lambda, which is called the wave number. Lambda here is the wavelength, so k is the wave number. So we get this equation, k squared phi plus phi xx is equal to 0. Furthermore, because we're very greedy, we will use the substitution phi node of x is equal to phi node of x multiply e power I s of x. Again, to use the s here can be regarded as a phase, because you know e power I sx is expanded equal to cosine sx plus I sine sx. So this part encapsulates the oscillatory behavior, and this is almost the amplitude. Okay. Again, we will substitute with this form inside this form. So we get this lengthy expression. Okay. First of all, k squared, here is k squared, phi, here is phi without any manipulations, plus this is second derivative. So let us just verify the first derivative. For the first derivative, you will get phi node comma x. This is derived, multiply e power I. I dropped s of x and just wrote s. Plus phi node as it is, get the derivative of this one, you will get e power is multiply isx. You will get the derivative of these using the product rule. This yellow term will generate two terms, and this green, it's like phi node e power isx will generate three terms, as you could see. And finally, we could collect together the terms having the imaginary part I and the terms that are real, and since this is equal to 0, we can equate the coefficient of I itself alone to 0 and the coefficient of the real alone to 0. Okay. Taking only the real part now, which we are interested about, we get this equation phi node k squared plus phi node xx minus phi node s squared equal to 0. And we can divide again by phi node, we get this expression. Now gets the most important and relevant part now. Again, it's a crucial step towards deriving Schrodinger equation. K is equal to 2 pi over lambda, where lambda is the wavelength. Fine. So we have here the wave number squared. If the wavelength is very small, then this fraction will be very big, and the k squared will be much bigger compared to phi node xs over phi node. Why? As a rough analysis, remember that phi node is simply proportional to the maximum value of phi node. Phi node xx, is proportional to the maximum value of phi node divided by z squared. What is z squared? Z is the typical or characteristic length. For example, consider the problem of light traveling along your room, okay, the room you are sitting in. The typical or the characteristic length for this problem is about 2 or 3 meters. However, the wavelength of the light is much smaller than this. So for this case, we can just use this equation as called the eikonal equation, k squared equal sx squared. Of course, for other cases, we cannot go through this when we are studying the light as a wave, the light diffraction and the light diffraction, for example, okay, and refraction. We will have to resort to the original, but for this one, it is very efficient considering geometric optics. Okay, and it is generalized in 2D, as you could see here. Fine. More explanation is provided in the next slide, again, without much more. In the next video, we will finish the derivation or the analogy with Schrodinger